Okay. Okay. Good morning, everyone. Today our first speaker is Professor Lei Fu from YMSA Tsinghua University. He will talk about an effective Deligne equidistribution theorem. Let's welcome.
我看听众都懂中文，所以我干脆就用中文讲，好吧，这样大家也轻松一点，我也轻松一点。哦，是这样的 ，OK， 那好吧 ，OK， so I will talk in English. This is a joint work with Liu Xujing and Xi Ping. So I think most people know Weil criterion. Suppose you have a sequence x1, x2 in R mod Z. Then you have the following equivalent conditions. The first one is the sequence is equidistributed. Okay, so that's the first condition. What that means? It means that if you consider the frequency of the sequence, okay, so you fix an interval, okay, for any fixed interval I, you consider the frequency of the sequence appearing in this interval I. And then at n goes to infinity, the frequency should be equal to the length of this interval. Okay, so that's the meaning of equidistributed. Sometimes it's also called uniformly distributed. Okay. This condition is equivalent to the following one. For any remaining integrable function I, if you calculate the average, okay, the mean value of the function on this sequence, and again you take the limit. The limit should be equal to the integral of this integrable function. Okay. For example, if you take f to be the characteristic function of the interval I, then the first condition, okay, then the second condition is the first one. Okay. If you take the function f, the integrable function f, to be e to the power 2 pi I kx, the exponential function, then again you can calculate the integral of this exponential function, and you find it's equal to 0 if this k is not equal to 0. All these three conditions are equivalent. Okay, this is the Weil criterion. Here is a very basic example. If x is an irrational number, then you consider the sequence nx in R mod Z. Then you can show this sequence is equidistributed. The simplest criteria to use is the third one, because if you take xi to be equal to I times x, then this sum is just you can use this sequence is an arithmetic geometric progression sequence. And you can calculate the sum, and then you find the sum, the limit is equal to 0. Okay, fine. Now, I'm not going to explain how to prove the theorem. Let me just explain one way to deduce deduce the first condition from the third one. Okay. Suppose we want to show this limit, the limit of the frequency is equal to 0. And I know this limit is equal to 0. That is, this exponential sum is equal to 0. So in order to do that, you have to bound this frequency by this exponential sum. Okay. This is provided by the Edwards-Turan inequality, which is proved in 1948. Turan and Edwards-Turan proved the following. For any sequence, okay, it might be a finite sequence, x1 to xn. You calculate the frequency of the sequence, okay, appearing in I, and then, okay, you expect it to be the length of this interval I, and then take the difference. The difference is bounded by the average, by this exponential sum, okay, by the mean value of the exponential sum. So divided by n, but there is an error term, m plus 1, but this m is any fixed, you can choose any m, okay. If you choose a different m, and then the sum here, okay, so k from, so k is, for this one, you have to calculate the exponential, you calculate the average of the function, of the exponential function e to the 2 pi kx, okay. But you sum over all those k from 1 to m, okay, And then here you have every term m plus 1 1 over m plus 1. To use this formula, okay, for example, you want to show this limit is equal to 0 if you know this limit is equal to 0. What do? You take a sufficiently large m so that 1 over m plus 1 is less than epsilon over 2. And then you let n be sufficiently large so that this sum is also less than half times epsilon. And then you find that this difference is less than epsilon. Okay, so that is Idle-Turin inequality. Okay. Now one of the main results of my talk is the following qualitative. You can think of Idle-Turin as a qualitative Weil criterion, but it is for this one, for this space R mod Z. R mod Z is a Lie group, the simplest commutative Lie group, one-dimensional, right? Okay. But then well, maybe most of the people know that the Weil criterion also holds for compact Lie groups. Okay, so I won't repeat that criteria or Weil criteria for compact Lie group. But let me okay. So here is our result, which is the analog of Idle-Turin inequality for compact Lie groups. Okay, like the GR be a compact connected Lie group. Suppose you have a sequence of conjugacy classes, x1 to xn. So GR lateral. So this notation means the space, the set of conjugacy classes of the group GR. Okay. Then for any small box D, I will explain what is the meaning of a D. So box is something like an interval for this compact Lie group. For any small box D, any positive integer m, which appeared here, but for different problem you choose different m. And then again we have this kind of estimate. What is this estimate? On the left hand side, you have the difference of the frequency with a measure of this box. Okay, I should say what is this measure? GR is a compact Lie group. So on GR you have the Haar measure. This Haar measure induces a Haar measure on the conjugacy classes. So mu GR laterally is just the Haar measure. The measure on the conjugacy classes is induced by the Haar measure. Okay, so we will bound this error, the difference, by exponential sum. But now you don't have exponential function on Lie group. What you have is characters. Okay, we know that every compact on a compact Lie group you have many irreducible representations. And then you take the choice, you get the characters for the irreducible representation. And here, those lambda goes over those irreducible representations. But there are infinite many irreducible representations. Just like if your group is R mod Z, then what is an irreducible representation? Irreducible representation must be one-dimensional. It is provided by a character. The character is exactly given by this exponential function. And so for each k, you have a character e to the power 2 pi k. Okay, but then here you have infinite many characters. You just work with those finite many. Okay, but here we have to fix a norm on the space of characters, and you consider those characters so that its norm is less than or equals to n. And then this is a character. I will explain these notations later. It comes from a Y character formula. Okay. Again, you have the characters. You calculate the average of these characters on this sequence, and then you have this kind of inequality. Okay. I will also mention what is the exact formula for C lambda. Okay. So you can see that these two inequalities are of the same type. Okay. So Idle-Turin inequality is for the Lie group, commutative one-dimensional Lie group, or torus R mod Z. For n-dimensional torus, this inequality is proved by Cochrane in 1985. And then of course, it's a natural problem to work with all the Lie groups. For example, how about SU2? For SU2, I should mention that the space of conjugacy classes of SU2 can be identified, okay, with the interval from 0 to pi. On the space of conjugacy classes, you have the Haar measure, the measure induced by the Haar measure. If you identify SU2 conjugacy class with 0 to pi with this interval, then this measure is identified with the saddle-Tate measure. Okay, so for SU2, the space is just 0 to pi, this interval together with a saddle-tate measure. For this measure space, this inequality is proved by literature in 1991. Strangely, nobody, as far as I know, in the published literature, no one work on compact Lie groups, even though it's a very natural question. You already know the result for SU2. You already know the result for all torus. Of course, the next goal is to prove such an inequality for general compact Lie groups. Okay. Now I'm going to before explaining the idea behind the proof, let me give an application. This application will give you, I'll call it an effective version of the Deligne equidistribution theorem. Okay. So let FQ be a finite field with Q element and of characteristic P. AO is a prime number distinct from this P. X is a smooth geometrically collected scheme over this finite field. And Kx is a function field. Let F be a lisse sheaf on X, lisse aodic sheaf on X. So if you are not familiar with aodic cohomology or sheaf, étale sheaves, then you can think F as a Galois representation. F comes from a Galois representation of the function field of Kx. Okay. Now the function field, so Kx is a function field of X because I assume X is geometrically collected. So if you base change X to its algebraic closure, you get another algebraic variety defined over the algebraically closed field. That variety, the function field of that variety is Kx FQ bar. And then you can consider its Galois group. It is a normal subgroup of the Galois group of Kx. And the quotient is exactly the Galois group of the finite field. Okay, so we have such a short exact sequence. Any QL bar sheaf on X defines a Galois representation of the function field. This Galois representation is unramified everywhere on X. Okay. Okay, so that is exactly a one-to-one correspondence. So we have an equivalence of categories between these sheaves on X and Galois representations unramified on X. Okay, so you can use different kind of notations for this object F. Now we have two notions here. Geometric monodromy group is what? Okay, so F is just a Galois representation. So its image, of course, if you consider its image, Galois group is a profinite group. Its image is a subgroup of GLV. So GLV is an aodic Lie group. Okay. So its image is a compact subgroup of that Lie group. Okay. But we want to work with algebraic groups. So you take the Zariski closure of the image of rho I. Then that Zariski closure is called the arithmetic monodromy group. Now what is a geometric monodromy group? Geometric monodromy group is you replace this X by its base change to the algebraic closure. Okay. So then you have the geometric monodromy group. In this talk, I will always assume the sheaf has a following property. The geometric monodromy group is equal to the arithmetic monodromy group. Okay, so that's my assumption. And also, you know that when I talk about equidistribution of a sequence, we have to work with a measure space. Okay, so and also we work with the compact Lie groups. They are all real manifold. Okay, but now if you consider our monodromy group, they are some groups like Lie groups, but they are algebraic groups, but they are algebraic groups over QL bar. But in order to talk about the equidistribution, you have to work with real Lie groups. And so we fix an isomorphism between the algebraic closure of the aodic QL of aodic numbers and the complex numbers. Such an isomorphism always exists. It is just an isomorphism of field. Okay, so it preserves addition, preserves multiplication, but it does not preserve the topology. On QL bar, we have this kind of non-accumulating matrix. Okay, on C you have this absolute value. Okay, so this is an isomorphism, just algebraic isomorphism, but not a topological one. But that's enough. Okay, we say our sheaf F is punctually pure of weight 0 if the following conditions hold. For any x, because your sheaf comes from a Galois representation, and that Galois representation is unramified at x. Okay, so you can talk about the Frobenii at that x because your representation is unramified at this x, small x. Then you consider all the eigenvalues of the Frobenii. If all the eigenvalues of Frobenii has absolute value 1, but you say the eigenvalues are just arithmetic numbers. How do you talk about its absolute value? You have to use this iota. Okay, you have to use this isomorphism to change an arithmetic number to a complex number. And then if it is 1, then we say if it is true for all eigenvalues for all point x, we say the sheaf is punctually pure of weight 0. Okay. Okay, now here is a theorem of Deligne and Grothendieck. Okay. So I combine two theorems together. I will explain. The identity component of this geometric monodromy group. Okay, geometric monodromy group is denoted by G. Its a connected component is denoted by G0. This group is a semi-simple group. Okay. Now what is a part of a Grothendieck? Grothendieck proves the following. If you know the geometric monodromy group is reduced, or maybe put it this way, if you know that your representation F is semi-simple, then Grothendieck proves this fact. The identity component of the geometric monodromy group is semi-simple. So that is the result of Grothendieck. Now Deligne proves what? Deligne proves that if your sheaf is punctually pure of weight 0, it is a pure sheaf, then as a representation of the geometric monodromy group, it is a semi-simple. Okay, so you combine these two theorems together, you get this fact. Okay, so we can always assume our geometric monodromy group, okay, has a semi-simple connected component. Okay, and also we have also the following fact. We have to change from the arithmetic space to complex mode. We have to change arithmetic representations to complex representation. Now we have the following equivalence of categories. Now you have a group G, it is an algebraic group over arithmetic numbers. And then using this isomorphism between algebraic order of QL and complex numbers, you can change a QL bar algebraic group to a complex algebraic group. Their representations, these two different types of representations, arithmetic representation of G or complex representation of GC, these two categories are equivalent. Okay. And also, we have to assume our group G, the geometric monodromy group G, is connected. Okay. So in my talk, I will assume this. Oops. Okay, I think that's it. Okay, fine. Now, to state the theorem of Deligne about equidistribution, I have to introduce more concept. Okay, denote the Lie algebra of GC by this frag G. Now, this Lie algebra is a semi-complex, semi-simple Lie algebra. Now, the H is B1 of its Cartan subalgebra. Cartan subalgebra is a maximal abelian subalgebra of G, and also its elements are all semi-simple. Okay, so that's a characterization of Cartan algebra. Now, Cartan algebra, because Cartan algebra consists of semi-simple elements. So every element, if you let every element H, X on G by the adjoint representation. Because H consists of semi-simple elements, this action is diagonalizable. Okay, so H acts diagonalizably on G. On the other hand, H is commutative. We know that if you have two operators, both of them are diagonalizable, and they commute with each other, then they are simultaneously diagonalizable. So the whole H acts on G simultaneously diagonalizably. Okay, what does that mean? Okay. Now so let me define what is the eigenspace of this action. Now for any capital H in the Cartan algebra, H, unite edge x on this Lie algebra G by this adjoint representation. And I want to find its eigenspace. I want to define what is the eigenspace. Now suppose the eigenvalue I denoted by the eigenvalue by alpha h. Then alpha h is the eigenvalue, the corresponding eigenspace is just this G alpha. Okay? So that this space is the eigenspace with eigenvalue alpha h. But I said that h acts diagonalizably on this Lie algebra. So this action is diagonalizable. That means this Lie algebra G is equal to the direct sum of these eigenspaces. Okay. When the eigenvalue is 0, I think this eigenspace is just the h. Okay. Cartan algebra is commutative. Okay. So eigenvalue, the h acts or commute. So this you get 0 eigenvalue. So G is a direct sum of that. But again, because this action is actually is a commutative, the action is simultaneously diagonalizable. So you have G equal to this one. But now the eigenvalue as h varies, alpha h varies linearly with respect to h. So each eigenvalue now becomes a functional. Okay. So that is a decomposition. Now those eigenvalues alpha, so that the corresponding G alpha is not equal to 0, is called a root. It's called a root. All these roots put together, you get the root system. Okay. One can show that the bracket between G alpha and G minus alpha is one-dimensional. Okay. Now, because it's one-dimensional, you can find a unique H alpha in this bracket, G alpha, G minus alpha, so that our H alpha is equal to 2. Of course, G alpha, G minus alpha lies in the Cartan algebra H. So H alpha is the element in this Cartan algebra. If we, actually, one can show that H alpha spans the whole H over complex numbers. But now I just take the real span. So consider the real vector space spanned by this H alpha. And also I choose an order on the root. Okay, so let me draw a picture here because later I also need to use it. The root system, okay, so the root system R is contained in the root system R is contained in the dual space of H, and it is in some it is symmetric. Okay, it's symmetrically distributed. Okay, I choose a generic or sufficiently general hyperplane passing through the origin. Okay. And then you will find some root will lie on the right-hand side of this hyperplane. And on the right-hand side, if a root is on the right-hand side, then I denote this part of roots by R plus. They are called positive roots. On the left-hand side, those roots on the left-hand side are denoted by negative root. Okay. And then one can show there exists a real Lie subalgebra of G, I denoted by GR, so that its Lie algebra also has a corresponding decomposition like this one. And let me just emphasize that here, this part is HR, is IHR, not HR. Okay, so you have an I here. Okay, so we have such kind of Lie algebra GR. This Lie algebra GR has a very special property. It is a Lie algebra of a maximal compact subgroup of G. How I denoted this maximal compact subgroup by GR. Okay, and IHR is the Lie algebra of the maximal torus. Okay, and one can show the following equivalence of categories. Complex representations of GC is equivalent to the condition to the representations, complex representations of the compactly group. Okay, so that is a very important fact because we are interested in representations of this semi-simple, complex semi-simple algebraic group. But it's not easy to do analysis on this one. But such kind of representations are in one-to-one correspondence with representations on compactly group. For compact groups, you can use many Weyl analysis. Okay. Okay, again, recall that at the beginning, I assume arithmetical monodromy is equal to the geometrical monodromy group. Okay. Now, for any x, recall that our Galois representation is unramified at this point x. So you have a Frobenius element fx. Frobenius element is a actually Frobenius element is not well defined. It's defined up to conjugacy. So it is an element it is a conjugacy class in the Galois group. Will the Galois representation, this conjugacy class in the Galois group become a conjugacy class in the arithmetic monodromy group? Okay, G. Okay, this geometric arithmetic monodromy group is an algebraic group over QL bar, and then I transform it, okay, to a complex semi-simple algebraic group. Okay, so Frobenius then define a conjugacy class in this one, but then one can use the theorem like such as Peter-Weil theorem, for compact Lie group. One can show that this conjugacy class in this semi-simple complex algebraic group. This conjugacy class define a conjugacy class in the maximal complex subgroup. But here I have to use the fact that our representation has a pure of weight 0. Okay, so that is a semi-simple part defined. So they have, because they have a complex absolute value, so they lie in this maximal complex subgroup. So the Frobenius element finally can be considered as an element as a conjugacy class in the maximal compact subgroup. Okay, but I should emphasize that it's not the Frobenius conjugacy class itself; it's a semi-simple part. Okay. Again, we have these Hard measures, and on the conjugacy class, we have the measure induced by the Hard measure. Okay. Now I can state Deligne's theorem. Deligne's theorem is what? Okay, it's the following. Deligne, when he proved the Weil conjecture, as a byproduct, he proved this kind of theorem. Okay. Now, suppose you consider all those rational points on this variety X, because at each rational point you have a Frobenius conjugacy class. Okay. And we wanted to find out how this conjugacy class is distributed. So you take a special domain, any domain, in this conjugacy class, okay, in this maximal compact subgroup or conjugate, okay. You want to calculate what is the frequency of the Frobenius of those rational point X lie, so that it's a Frobenius lie in this domain D, okay. And then when n goes to infinity, this limit goes to this measure. Okay, so that is the equidistribution theorem of Deligne. It's somewhat like Chebyshev density theorem, okay, in higher dimensions for compact Lie groups. Okay, well, we know that for finite Galois extension, the Frobenius is equidistributed. So the Frobenius lies in one conjugate class. What is the frequency? It's equal to the number of the conjugate class divided by the number of elements in the Galois group. So it's a similar type, but this is a higher dimensional. Okay. Now we want to have an effective version. Okay. We know this frequency is approximately equal to this measure. What is the difference? Can you estimate the error term? Now here is the error term. Okay. Now error term looks a little bit complicated. You have this Q. Q is just the number of elements of the finite field. You have Q to some power as a log term. Okay. What is R plus? R plus is just the root, the positive root, the number of positive root. Okay. So this is error term. Okay. Let me explain how to deduce the Deligne's effective version of the Deligne's theorem, okay, by the Adolph-Thoran type inequality that I mentioned at the beginning. Okay, so now I need more concept from the theory of compact Lie groups. Let NT be the normalizer. Okay, T is what? T is the maximal torus of this compact Lie group GR. Okay, we take its normalizer. T may not be normalized. It's not a normal subgroup of GR, but we take its normalizer. Now it turns out that T has a finite index. Okay, finite NT over T is finite. It's a finite group. Okay, so this group is called the Y group. The Y group acts on T by conjugation. Okay. Because it acts on T by conjugation, it also acts on the tangent space of T. But the tangent space of T is the Lie algebra of T. The algebra of T is IHR. So W acts on HR. Okay, it acts on the Lie algebra, acts on HR, and also on the dual space. Okay. And then using the structure of the semi-simple Lie algebra, you can provide some inner product on this Cartan algebras that are given by the Killing form. And then W, our definition of W is defined to be the normalizer of the maximal torus model, the maximal torus. But there is another more combinatorial definition of the Y group. Y group can be identified with those also, it is a subgroup generated by reflections. Okay, reflections with respect to some hyperplanes. Now, what are those hyperplanes? For each root R, I have defined HR. Okay, so you take the orthogonal complement of HR. Using this orthogonal complement, you get a hyperplane. Then you take a reflection with respect to this hyperplane. You get a linear map. Okay. A linear map of order 2, okay? And then the Y group is generated by such kind of reflection. Another important fact is the following. We are interested in the distribution of a sequence in the conjugacy classes of compact Lie groups. Our compact Lie group is where, its structure looks very complicated. Of course, the space of conjugacy classes is even more complicated. We want to have some simpler model for it, okay? And now you have a torus T. I said that the Y group acts on T. How? Okay, suppose you have a GT, so X is an element in T. G is an element in the normalizer, okay? So G acts on this X by the conjugation. But now this X and G inverse, they are conjugated to each other, okay? So W preserves this action preserves the conjugacy class. So we have a map which maps each element T, for example, I want to use X. It maps each G. Okay, you map each G to its conjugacy class, but then because W preserves this conjugacy class, so you got a map from the quotient space T mod W to this conjugacy class. It turns out that this is a homeomorphism. Okay, so instead of studying the equidistribution of a sequence in these complicated conjugacy classes of compact Lie groups, you can consider a simpler one. You can just work with a torus. A torus is much more simpler. Okay, much more simple. Okay. But a torus is not enough. You have to model out by a finite group W. Okay, so that makes things a little bit more complicated. Okay, fine. Now let G, I have to state some fact from representation theory. Now suppose G is our semi-simple algebraic group. Suppose you have a finite dimensional irreducible representation, and then denote the corresponding representation of Lie algebra by this notation, small g to GL, small gl. Because the representation I said a moment ago, so I should add here, this capital H, so this capital H, so I should write V lambda equal to V H V equal to lambda H V for all H belongs to Cartan algebra. Okay, so let me emphasize that H, this capital H goes over small h, goes over all the Cartan subalgebra. I said a moment ago that Cartan elements in the Cartan algebra are semi-simple. Because they are semi-simple, they always act diagonalizably on V. Okay? Because they act diagonalizably on V, so you can decompose V as a direct sum of eigenspaces. But because H is abelian, so they are all these actions are simultaneously diagonalizable. So you can find a family of eigenfunctionals. Okay, and put this with lambda. Okay, for each lambda you define the corresponding v lambda, that is h v equal to lambda h v for h. Okay, then v is equal to the direct sum of v lambda. So each v lambda is an eigenspace, and each eigenvalue lambda is actually a function. Okay, all those lambda so that v lambda not equal to 0 are called weight of the representation. Okay, so give you a representation, you have many weight, and this weight in some sense also distributed on this space. This space is H star. Okay, and among this weight, some weight is called maximal weight, highest weight. What is the highest weight? Okay, when I define an order on the root system, I choose a generic hyperplane. Okay, on this way, okay, there are many weights. Okay, some weights lie on the right hand side, some weight lies on the left hand side of this hyperplane, of this chosen hyperplane. There is one, okay, lies on the right, which is foremost, okay, which is on the right, and its distance to this hyperplane is the largest. Okay, so that one is called, we call it the highest weight. Okay. Okay, some other fact. We know that on T, its Lie algebra is I times HR. Okay, and I write it as 2 pi I times HR. Okay, they are the same space. We have the exponential map. For torus, the exponential map is always an epimorphism. Okay. Now the 2 pi gamma b is kernel. Of course, the kernel is a full lattice. Okay, gamma is a full lattice of HR. We call this lattice an integral lattice. So then through this exponential map, you get an isomorphism T with HR mod out gamma. It's just like you can think S1, the one-dimensional torus, one-dimensional circle, is just R mod Z. Okay, R mod Z. For any weight lambda of the representation, okay, so here is the fact. For any weight of the representation, we have lambda gamma is contained in Z. Lambda gamma is contained in Z. So what is the weight here? The weight means it's the weight in this one. So we have any kind of, for any representation of the semi-simple Lie group G, for any weight lambda for this representation, we always have lambda gamma is contained in Z. Okay, here is a fact, and it can be proved. Okay, it's not a hard fact. And I denote all those functionals lambda, so that lambda gamma is contained in Z. I put all those functionals together, denoted by I star. It is called the lattice of integral forms. Okay, so we just have two definitions here. Okay, now for any such kind of lambda, that is lambda gamma is contained in Z, you can define a representation of T. You just map e to the 2 pi h to e to the 2 pi lambda h. Because lambda is a functional, okay, lambda function on HR, so it acts on h, okay, e to the 2 pi h. And, but well, is this representation well defined? It may happen that in one element in X, you have several ways to write it as exp 2 pi h, okay. For example, if your h lies in the kernel, then e to the 2 pi h should be equal to 1. The right hand side should be equal to 1. Why it can't happen? Well, if h lies in kernel, because your lambda is very special, lambda maps z gamma to z. So if h lies in the kernel, that means h lies in gamma. Then lambda h lies in z. E to the 2 pi z is an integer, it's 1. Okay, so this is indeed well defined. It gives you a character of T. Actually, all characters of T are obtained in this way. So I star you can think as a character group of this maximal torus T. Okay. Now I have to state more fact here. A moment ago, okay, I mentioned that we have. Okay, let me put it. Jump to this place. At the beginning of this talk, I said I'm going to show you either Turan type inequality. Okay, on the left hand side is the frequency of a sequence appearing in a box, interval, minus this measure of this box. I wanted to bound it by some character sum. What are